Yes, I think we are live. Hi, everyone. Welcome to another learning session of the IoT Space Challenge organized by hubraum, the tech incubator of Deutsche Telekom, together with the European Space Agency. I'm happy to present our last learning session to you. And before that, for the ones if it is for your first time joining our sessions, I would like to talk a bit about the IoT Space Challenge. So, IoT Space Challenge is a brand new program where we are seeking for the teams with expertise in IoT and Earth observation and willingness to bring these two technical domains together. And we are looking for startups, developer teams, and companies with like a more mature stage. So ideally, you should have tested your MVP in a real life setting. And this program is very interesting. And I like in the first 3 sessions, I always counted what you get, the ones that you see here. But I think the most important thing that you are getting out of this program is that you get the chance to collaborate with Deutsche Telekom and European Space Agency and work together with the experts in these two domains. So, which is very valuable for a startup in this incubation phase. That I think it is a no-brainer that you should consider that program. But on top of that, there are also more tangible things that you're getting out of this program, being up to 6,000 euros to sponsor creation of your selected use cases, IoT creators connectivity and network expert support, plus IoT prototyping kits for getting started with IoT use cases. You get access to European Earth observation data with ESA access port. You get access to Copernicus data space ecosystem that was mentioned in our second learning session. You get access to hubraum campus spaces in Berlin and Krakow for working and prototyping. You get AWS credits if needed. You get potential co-investment by hubraum fund up to 1 million euros, and you get the opportunity to join larger ESA incubation programs. So if this program is interesting for you, you are always encouraged to apply from the link below. And so the application deadline is our program is actually getting closer. We have 10 more days, and the deadline is March 31st. So I will continue to remind you also at the end of the session. But if you are working in one of those domains and these topics are interesting for you, you are welcome to apply. And I also see some familiar faces. So maybe some of you joined also our previous sessions. So in the first 2 sessions, we deep dive in the specific topics. First one being IoT and the second one being Earth observation with Copernicus data space ecosystem. And Frank bring these two topics together with satellite IoT. And Valentine today will wrap these two topics up by explaining the use cases and applications of IoT and space. And we are very glad to have him here, of course. And very briefly about today's session. So it is about the use cases and applications of IoT and space. And we are planning a 60-minute session, including the Q&A. So your questions are always encouraged. Please use the Q&A feature of LinkedIn. And yeah, I will ask your questions, read them out loud at the end of the session to Valentine. And so this session is also recorded and can be found in the hubraum's LinkedIn page, as well as the program application page that you have the link below. So if you missed the previous sessions or if you want to go back to those, you can find the recordings there. And yeah, final one more call to action for our program is you can see the QR code here. And if you're interested in being part of this program, you are always welcome to apply. And with that, I am handing the word over to you, Valentine.
Thank you, Jensen. So my name is Valentijn Venus. I work for a spin-off company of the University of Twente, faculty for geoscience and Earth observation. And it's a pleasure for me to meet you and hopefully get to know you better as part of this program's period of the next couple of months, as we dive into where IoT and space indeed could potentially come together. So this is just an appetizer to inspire you. Hopefully, there will be lots of creative juices flowing in the months to come. So today, without ado, a couple of applications of IoT and space, and potentially where the sum of these two is larger than their individual components. So here we go. So again, today's session wraps all of the previous up, but as Johnson said, feel free to revisit the previous ones which were recorded. So looking at sort of this global development in space technologies, we are in this unique situation where we're sort of hinging on all the more scientific space missions that were run until a couple of decades ago, all the way up to recently. We're now in a more mature, if you like, phase of data accessibility, which was also thanks to all our European investments, but also all the ESA member states contributing to new observing capability from space. And you are in this unique generation of hopefully new innovations where all these throws of freely accessible data are now meaningfully combinable with IoT sensors to help address some societal challenges. So let's look at what the Copernicus program looks like. So in a nutshell, we know this is an effort to create sort of a time machine, an eye in the sky that at the same time functions as a time machine of where we are coming from, and with digital twinning technology becoming more common, also projections of where the Earth as a system is going to and how we can potentially capture these critical tipping points in potential climate change, or even individual scheduling of irrigation by farmers, all the way up to how the long-term ensembles of the future climate change, but also other phenomena are likely affecting our daily lives. So let's look at some of that trove of data. It is free, full, and open for a very long time to come, and already for a significant period. And thanks to recent changes that were also introduced to you by Yuri de la Mar, this data access, having all of this satellite imagery at your fingertips, is going to extend in the next 10 years and beyond. Now, having laid this foundation of clarity about data access and free of use, let's look at some of the programs. So we've got the Copernicus Sentinels here, 1 to 6, including some newer missions that are about to be released. For example, there's a new high-resolution thermal imaging mission starting with capabilities to monitor land surface temperature in a fragmented heterogeneous landscape very soon. And of course, we're also very happy with the different dimensions of these and unique complementary characteristics of these satellites, such as radar vision, being able to penetrate through clouds even at night. Sentinel-2 with its unique optical band positioning around the red edge to allow for example, chlorophyll concentration retrieval in canopies. Sentinel-3 giving us this global picture of the oceans and ocean color conditions. Sentinel-4 with its diurnal unique sensing capability, potentially yielding observations of the whole of Africa and Europe every couple of minutes. And then, of course, partly a Dutch-built sensor, the Sentinel-5P Global Air Monitoring Mission, with finally Sentinel-6 to observe the changes of our climate on the global Earth's surface, but also sea level rise. Now, all of these observe land masses every couple of days at currently the best optical resolution or horizontal spacing of the pixels at 10 meters. And this is a significant amount of water flowing through the river, up to 250 terabytes of daily data. And luckily, there are now mechanisms that you don't have to put your cup in the river every day to catch the water but there are long-term archives which you can rely on, and services to make your data access even simpler. So in a nutshell, we see the different science programs that started decades ago and sort of where there's a runner-up to the more operational missions in the blue area, and then you've got this unique category of meteorological missions, which, because of the urgency of weather information, have already traditionally received much operational attention, but now also these scientific missions offering a trove of data that offer also very new use cases that we potentially could address. So let's look at that one as we go forward. So all of these slides will be available for your consumption at a later stage. So let's look at the aspects here, the physical quantities that we are able to observe through these different Sentinel Earth observation satellites. Now here you see an example of where Sentinel-1 and 2, so the optical and the radar, are jointly used to create accurate mappings of different crop types and to be able to monitor those across the season. Now note the legend in the graphic that was kindly contributed by Vito, the Flemish research organization having a key role in land monitoring product generation. We see that there's much more information in detail than traditionally we see in, for example, the Corinne land cover map. We are able to discriminate even between winter wheat and winter barley. So that's a new type of discriminative power, which is very helpful, of course, in creating an information system. Of course, beyond the use cases of monitoring smart farming, even within field variability, and we'll talk about that, lies amongst the possibilities. But we all realize that satellites from, say, hundreds of kilometers from the Earth's surface have a thick atmosphere in between them. And that in itself tends to degrade the signal-noise ratio. And so there are certain situations where this distinct discrimination capability based on unique radiometric wavelengths or other features are somewhat obscured by the atmosphere itself. And so also clouds, which you sometimes do not flag correctly. So it is quite helpful to think of IoT devices that are sensing the Earth's surface or the boundary layer of the atmosphere at a much closer distance to help triangulate between these signal-noise ratios and find ways to overcome each other's weaknesses. So here you see an example of how that capability can then be a dashboard. So here in the top panel, again, an image of a Sentinel observation over an agricultural field. We can also in the variability within the plot see that based on texture or past compaction or potentially even cultural, historical activity in this parcel, there is differences between the within plot surface area. And that's very helpful for, say, high precision farming to allow for a better balance between inputs, fertilizers, for example, and the outputs, so that you don't over-fertilize, where, say, soils are a bit clay richer and are able to cling on to the nutrients that you apply much better than the coarser sandy soils. In the bottom panel, you see the temporal dynamics within and between years, which is again very helpful to have this time machine from space to be able to judge whether or not, based on a model of analogies, previous years are in a repeat, or we clearly see a deviation from the long-term average. Also to be able to judge again, you see the green dots not perfectly aligning with the curve-fitted phenological progression. Also to judge whether or not we're looking at noise in a signal or the signal in the sensor observation. This also allows you to set triggers, and you see here the threshold for, say, something that needs a remedial action, perhaps irrigation scheduling. We'll talk about that more in a minute. Previously, this was only possible at, say, kilometer resolution. And luckily enough, thanks to the enhancements and the operationalization of these scientific missions, we're now at resolutions that are able to capture both the between day, but also within field variability. Well, more about what you can do with this information. You here see a temperature anomaly map for Europe for a particular season. Now, for any particular location within this image, I can run a digital twin of the farm, if you like, that allows us to see the progression of a canopy, in this case, a maize canopy, producing, say, fodder for dairy cattle. And you see here the progression is initially very positive, with the green curve following what we expect, a logarithmic growth vegetative phase. But then suddenly you see there is a dip in this green curve, switching from growth to actually decline. Now, this is caused by lack of water in the soil, in the easily accessible water for crops. Obviously, we account for the rooting depth of a plant, and you see that there's an extended period of drought where the actual evapotranspiration is much lower than what the plant could potentially transpire and evaporate. Now, this is modeled as a function of the closure of the stomata of these plants. In actual fact, farmers in the Netherlands do this kind of near sensing of canopy temperatures using the touch and feel method. They just hold on to the leaf, and if the leaf is not significantly colder than their skin temperature, they know there might be a problem. This should be colder, because transpiration itself is a very endogenous energy consumptive process where water molecules change their phase from liquid to gaseous, and that extracts huge amounts of energy from the canopy. So canopy should be cold, so it's quite alarming to see a warm canopy. Now here you see that process in more detail and some of the underlying physics behind it. And to prevent dehydration, the leaf tissue just closes its stomata to prevent dehydration and death. But in the process, as it closes its ability to exhale oxygen and exhale water, it automatically also proportionally reduces the amount of CO2 molecules that it can intake to support its own growth. Now, that in itself is useful information, because you want to prevent this by all means. So farmers are now finally able, with this digital twinning capability, with the information provided by the Earth observation program of the Copernicus program, to schedule the water supply and potentially even the quality of the water, so the salinity of this water, which is, of course, in an ever warmer climate, becoming increasingly important to understand that we don't want the wastelands of Mesopotamia in Europe or in Italy, as we saw last summer how dry the irrigation schemes were. Then obviously salt starts to increase, and as salts increase, the drought effects are even more pronounced. So this is something to worry about and something to monitor. More about that in a minute. In the second panel, you see the land surface temperature, not only from a polar orbiting satellite, which obviously has the added advantage of having a higher horizontal spacing or better resolution, But here in the second panel overlaid, you see also the geostationary satellite that follows the same observation on the Earth's surface. So it's able to make photos, say every couple of minutes even, scanning the whole of Europe and Africa, potentially being able to observe just when clouds are passing by or have passed by, just to make sure that we get this diurnal progression of drought accurately. Another example of that same physical and technical capability is then here shown, where we're not only capturing soil and soil moisture variability, but also the total amount of leaf mass above the soil, which is quite important, obviously, as leaves within a vegetation canopy form the solar panel, and without solar panel, you can't harvest the sun. So again, this is quite an important contribution in terms of geophysical parameters that we can estimate from, say, Sentinel-2 and 1, including also very useful for irrigation management and scheduling the moisture within the soil, which obviously is depending on soil texture, organic matter, which is highly variable and difficult to map. But now having direct estimates of soil moisture is a beautiful shortcut going straight into the observation or unique observation capability of satellites. Precision farming and irrigation here again illustrated. Now, irrigation on demand is obviously something also in high favor by, for example, the likes of Unilever and other global food producers and commodity producers, which, because of their fragile and important brand and brand recognition, by all means want to prevent their so-called overuse of water in producing, say, cereals, to somehow put their brands in a bad daylight. So that even Unilever has been very interested in this capability of IoT sensors and Earth observation capability to, at large scale, monitor small scattered fields of all their contract farmers without the need of expensive sensory capabilities. Now, or consultancy services that have to go into the field and charge by the hour. Now, the unique capability of Sentinel-2 is here illustrated, where there are unique radiometric channels in the red edge position, as we call it, of the electromagnetic spectrum, which allows us to, based on the angle of the red edge position and the absorption features therein, is to estimate the nitrogen canopy concentration, which is, of course, a unique capability to also schedule precision fertilization, which is, of course, in the context of the current European Commission's transition to a more sustainable land use practice, key in making sure that we have not only drop for crop, but even grain of fertilizer for crop. Another example of where Sentinel data potentially could augment IoT sensory capabilities is, for example, in this subsidence process of, well, either as a result of natural extraction of coals or gas from the deep earth surface layers, which tend to, in the end, result in compaction. We still see a continuum of the same phenomena in the Ruhrgebiet and in the northern areas of the Netherlands of these extractions. But also in the city of Amsterdam. As you know, the city of Amsterdam is built on poles. So all these houses rest on the stability of wooden long poles. Now, with lack of maintenance of this 17th century canal ring, the UNESCO's World Heritage Site of Amsterdam is at jeopardy of collapsing and of course, in the process, threaten the value of real estate and tourism. Now, this is a long stretch of canals to monitor, hundreds of kilometers in total. The problem is renovating 1 meter stretch of this area in the cultural historical center of Amsterdam will cost the municipality of Amsterdam roughly 35,000 euros per meter. Well, that cost exceeds, if you multiply that times the number of bridgeheads and the kilometers of quay walls to be restored, that well exceeds the budget of the municipality, and therefore they have to have a tool to prioritize which buildings and bridges are most at jeopardy. So it would be wonderful if we could have the eye in the sky, for example, Sentinel-1 aperture synthetic radar observations, or INSAR multi-temporal techniques to find these subsidence deformation hotspots, millimeter accurate, and then have IoT sensors to overcome some of the sensor signal noise ratio problems as is apparent from this scatter plot. So today, there is no monitoring platform to help the municipality. Another example, of course, where IoT-based technology and Earth observation technology could complement each other is the monitoring of our global water demands. With only roughly 1% of our blue planet's water easily extractable, we have literally a treasure hunt for scarce fresh groundwater. And well, that confounded by multiple negative impacts from sea level rise, subsidence at the coast, intensity of droughts, and increased water consumption. This is certainly an urgent issue and to be further explored. Well, with 30% of our global population living within a 100-kilometer buffer of the coastline, you can imagine how important fresh water is for sustaining food baskets and securing the SDG of food security. When we look at some of the capabilities of satellites, they are also able to see the opposite, namely too much water. Here you see a simulation of or the mapping process of the flood events in Australia here in the month of April 2022, where we see a combination of Sentinel-1 and higher resolution capabilities being used. More R&D types of applications, it's not just about the water, but it's also about the water quality, as we talked about in the digital twinning of a farm. So we need to know the salinity of this water, whether or not we can either extract it for human consumption or for industrial or agricultural purposes. So here you see an experimental sensor capability that has this unique profiling of salinity up to sometimes 80 to 150 meters depth. So you get this three-dimensional data cube of salinity levels. And traditionally, with IoT sensors, we could only see the surface area of, say, these canals between agricultural plots. Now, having this UAV-borne or helicopter-borne, and potentially in the future satellite-borne salinity sensor, you can go up to into the 3 dimensions of the Earth. In addition to the subsidence application that we talked about earlier, this synthetic aperture radar capability can also help, as we talked about earlier, soil moisture, albeit at variable accuracies and only at the soil's surface. And of course, that's where also knowing that water and moisture distribution in the vertical direction of the soil is highly dynamic, depending on capillary rise capabilities, which is again a function of texture and other factors, and or any unpermeable layers. It's a huge challenge to map this accurately. So it would be wonderful to have data sets from potential IoT sensors to overcome some of these weaknesses that the eye in the sky unfortunately sometimes comes with. And we could, of course, explore deep learning approaches to accelerate this process of easily extractable fresh groundwater to potentially global scales, to inform water management and to minimize desalinization risks. Another example of Sentinel-1 data, for example, enabling rapid detection of small-scale forest disturbances. We talked about the logging and subsidence in agriculture, but increasingly so global alerts for better wildfire detection have only become more pressing as we've seen the impacts of our dry summers. Now, subsequent observations could be used to increase the confidence and or to confirm or reject an alert if we also combine this with IoT sensors. So let's look at that use case. So when forests burn, vast amounts of stored carbon is emitted to the atmosphere. Now, when the vegetation then, of course, goes through a regrow phase, successfully, it just draws back this carbon that it emitted earlier and stores this back into its woody biomass. This is, as we all know, a part of the normal fire recovery cycle. And of course, over many millions of years, species have grown to evolve and adapt to these cycles of fire and then moist conditions. And so there's not really something special about it, perhaps only to say that it, of course, may be posing dangers for the demography living in these areas, but it is part of our natural cycle. But what is really problematic is somehow if we reach what we call a climate or microclimate tipping point, where suddenly these sinks, these forests or sinks of carbon dioxide may switch to carbon sources permanently. And of course, we have seen these publications recently of the recovery of the Amazon forest still not matching its previous carbon sink capabilities. And so it is key for us to be able to simulate the usefulness or fit for purpose of Earth observation and IoT sensors in this context. How do you and where do you position these IoT sensors to capture the microclimate and capture these tipping points accurately? And so, of course, also emergency and response services in cases of wildfires are served by better strategizing of where to place IoT sensors. Here you see a simulation of what a fisheye camera would see at a certain position in the forest. Well, with recent game engine technology and augmented reality, these visualizations have only become more useful. Another example of how forest monitoring is made useful using Earth observation, in this case in a forested area in Germany, the Wald biomass trend, so the biomass in the forest being mapped thanks to the capability of Sentinel-2 and Sentinel-1 data. And it's almost semi-automatically, which is quite important because subsidy programs in Germany, for example, are tied to proper reporting. So the owner of this forest is only able to substantiate a claim for a subsidy for reforestation, for example, if there is evidence of the same. Pardon me. Another interesting example of digital twinning technology is here illustrated that we can even simulate satellite images themselves without launching a satellite into orbit necessarily. You can already see what the satellite would see. Why is this useful? Well, it's also often the first step that I, as a researcher, go through. We first go into the dark room, as we say, to check whether or not the radiometric discriminative power, for example, is proven on on a dark lab or a lab level before we even think about downloading satellite images. And so even more so important when you design a new satellite. In this case, it would be wonderful to have an eye in the sky that could see starting forest fires, say the forest floor. And here you see the simulated radiative response of a forest fire starting on the surface of the floor, and what parts of the radiometry are being affected from potentially unique or discrete angles, as satellites also have the capability to observe in discrete unique angles. And of course at different pixel sizes and whatnot. So this is of great help to plot whether or not Earth observation in the future could become even more useful than it is today. Or whether or not an IoT sensor could be designed to capture certain parts of the electromagnetic spectrum. In addition to vegetation volume and health and changes therein over time and space, we already understood that the radar satellites can penetrate clouds and see moisture levels not only in the soil but even in the canopies of forests, which is key to predict and to model wildfire spread digital twins accurately. IoT sensors below the forest canopy can see where satellites cannot see yet, and so soil moisture profiles or positive anomalies in soil moisture in certain areas can help to reduce wasting attention of forest fires and focus their attention to areas that are more prone or at risk. Again, deep learning approaches can help to scale this and automate this and find these tipping points as we discussed. This is also a potential case where IoT and AO together could have a value larger than its individual components. Radio waves flow from a transmitter to a receiver, but this depends on many factors such as the relief of the land surface, the various obstacles, as well as the land cover and land use. So Earth observation sensors can capture this radio cluttering phenomenon to create a spatial and temporal picture for better IoT deployment and planning purposes. So again, how do you map the best configuration of multiple IoT sensors that are networked together and talk to each other or use each other's capabilities to relay information to the next sensor when there are no relays or dedicated relays? You need to really plan this accurately, and you need to know the radio cluttering to minimize signal loss due to these obstacles and attenuation. And this is a kind of map that you can produce with Sentinel data to understand this radio cluttering and where, if you want to go through the forest, at what spacing IoT sensors have to be placed to be within their spec of radio communications. Here you see in a histogram plot the same amplitude in radio attenuation or dampening for different seasons or cycles. The IoT sensor can capture information, for example, from phenomenon below the forest, as we just saw in the previous example, but we could also introduce capabilities on IoT sensors that, for example, using radio acoustic remote sensing techniques, map the thermal landscape even in the height direction of the forest, allowing us to do a continuous thermal characterization of a forest area for near real-time fire detection and characterization. So here you see the Earth observation sensor observables influencing the way you should plan your IoT radio network. And on the other hand, you see IoT sensors can provide at the same time information that we can't see with Earth observation or can't tell accurately enough. So you could deploy algorithms such as a free line of sight based on a DAM combined with the height of the trees or land cover to have a true digital terrain model to produce more cost-effective IoT networks, knowing that trees attenuate differently with dense coniferous pine forests versus, say, normal broadleaf forests. So as a rule of thumb, for example, 10 meter of mixed forest is equivalent to 2 dB of attenuation at different wavelengths. Now, then the Earth observation data becomes an aid, an asset, a utility for planning your IoT sensors. So the two can help each other, and planners can accordingly select a different latitude, longitude, or location for IoT sensors to make sure that these weaknesses are overcome, both taking into account summer and winter. When the blue and the red curves, when they differ, it means that the denseness of the forest between summer and conditions, the phenology cycle, are significantly different. And when they are very close to each other, or when there's only one curve, there's hardly any phenological difference. So also no difference within the months of the year. But if there is a difference, such as in panel C and D, it really serves to start using Earth observation data in a better planning of your IoT radio network. Till date, there is no operational service for this, so this is another business opportunity. Another interesting example, of course, as we have seen with this unique with and without industrial activity and traffic, thanks to, well, indirectly, the lockdowns, we now know what is the true anthropogenic impact on Europe from emitters, and we can now, thanks to Sentinel-5P, see, for example, not only the dust in the atmosphere, but also NO2 tropospheric column retrievals. This is, we know, a serious cause of casualties as well, with many premature deaths as a result. This is obviously of interest to also the health community. And there are increasingly new calls and tenders to combine Earth observation data with geo-health, as we see. Well, again, here we are, for example, interested in the point source causalities. So again, if you take a company like Tata Steel to court, you better come with proper evidence. So again, IoT sensors are very useful in such use cases. Here you see again an example of this unique sensing capability. And you see also the spread from the point, the smearing of some of these larger cities in France, for example, from Paris and Lyon. But similar patterns we see in Western Europe between the Netherlands and West Germany. So we, in a way, are now seeing exactly what we inherit from each other. And another inheritance is our use of oil palm as a replacement substitute for, say, the increasing prices of our sunflower oil that is becoming scarcer thanks to the civil unrest. And here you see also the negative side effects that can have on endangered wildlife species such as the orang-outang. A mother orang-outang spends on average 600 days teaching her offspring what fruits in the tropical forest can be eaten and which are poisonous. So all this training goes to waste if we somehow drain the moisture in the soil and deplete it to create better conditions for agricultural productivity, and in the process increase the dangers of wildfires. So this is a unique contribution from the Copernicus missions also to help NGOs such as the one supported by Leonardo DiCaprio to help protect this fragile ecosystem in Indonesia. So yeah, the unique offer of this program, there is not a single source of donation that is more prosperous and more generous than any startup could receive than this free trove of satellite data to be thrown in your lap. It's a unique service that, with the clarity of more than a decade to come of data provisioning, compute service, data storages, services, this is too good to be true. And this is the only time it's really true. So as a startup, if you want to have some cash injections, well, just tap into the Earth observation data services from the Copernicus services, and you have received an investment of over 10 billion, probably, as you accumulate your Earth observation image consumption. You will only increase the amount of assets you've brought to good use in be it natural resources, energy transition, defense, finance, infrastructure, etc. So with that, I would like to welcome to be part of this already more than a decade of innovation competitions at the European Space Agency, from the likes of the Copernicus Masters to the Space App Camps. We are very excited to partner T-Mobile and other partners in this challenge. And we look forward with you to make an impact. And I'm available and at your disposal to guide you through the different steps of your ideation and trying to understand the fit for use of Earth observation. This was my contribution. If there are any questions, feel free to ask.
Thank you so much, Valentijn. It's Megan, and really you gave a lot of great ideas and honestly some business opportunities for the startups. So they can just, if they really listen carefully, they can just grab your ideas and bring a solution for that program. But thank you so much for sharing your insights. And now, we have some time for questions. I see some in the chat. So also you can see it on the screen. So the question is when we should do the digital twins for the images?
Yeah, I would say almost always. You should always go back to the underlying physics of the problem that you're trying to solve to try and make sense of where potentially radiometric, unique, discriminating features could lie. And if you don't see uniqueness in the, say, the radiometric spectrum or the radar attenuation phenomenon, then why bother downloading all sorts of images and hoping you will find a needle in a haystack when you don't have the, say, the theoretical sound evidence that there is discriminative capability?
Thanks for your answer. Hope this helps. If not, please continue asking in the chat. And actually, I do have a question to you, Valentijn. So you mentioned all the advantages and like the potential use cases of these two fields being brought together. But what do you think are the challenges of bringing these two fields together? Do you see any challenges on the way for the startups?
Yeah, of course, when you bring together multiple disciplines, there is this issue of the Babylonian confusion. We speak different languages, perhaps express or don't even mention expressing the units in which we measure certain phenomenon. So that's also where we will help guide you to use semantically enriched data models and data structures to make hundreds of pages of PDF documents that you can read and summarize them in just a few sentences with just the key parameters about, for example, the signal noise levels that we talked about earlier. And temperature sensor itself is only an estimate of reality. And probably if you take a temperature sensor or a thermometer that was built for human consumption, you take it to the North Pole, probably there are not even indicators at that part of the actual temperatures to read out the value from. And let alone all the increased uncertainty at, say, extreme high or extreme low temperature. So all of this is hidden in large, big PDF documents. We hope to bring this to the surface so that you can make sense of how data is combined, and indeed whether or not IoT observations have this unique discriminating feature to overcome, say, the Earth observation data's weakness and vice versa.
Yeah, exactly. And I think there our program really comes to the play, and the having the experts in these both fields would make it easier to bring those fields together and overcome those challenges. Yeah, being this 1,000 pages of PDFs or many other, as you said. So thank you so much again, Valentine, for that session. I am sure it will be greatly helpful for the program startups and for everyone that is interested to learn more about these two fields coming together. And for the one last time, if you're interested in joining our program, here is the application link, here is the QR code. And if you have any questions to us, you can also contact us via hubraum's pages, and feel free if you need more direction on our program. We are always happy to help. Thanks for joining the session, Valentine. And yeah, looking forward to working with you also during the program.
Likewise, look forward to seeing you again. Good luck with the submission and have a good evening.
Thanks a lot. Have a good evening, everyone. Thank you for joining.